Hello, and welcome to this lecture on testing our object dimension functionality. Congratulations on getting this far again. We are getting through this course now, and you have essentially created yourself the fundamental structure of a directed acyclic graph, which is incredibly impressive. And I'm hoping that you are understanding how impressive this is if this is your first dive into kind of seriously making a Python framework for any code structure, because you could use this again. This is a good structure, but this isn't just applicable in Maya. You could apply this kind of methodology to machine learning algorithms. You can apply this to pipeline setups. You can apply this to app development. This kind of setup isn't really just for this type of programming. It's a type of programming which increases efficiency and overhead within your general structure. So you should look at this as a massive step up for you as a developer, and not just a rigger, not just as a CG artist, but you should look at this as a massive step up for your knowledge and its applicability to lots of other forms and lots of other areas. Because again, the only way you're really going to kind of increase your knowledge is by essentially branching out, trying new things, learning different frameworks. It's the best way to learn some really interesting stuff. But okay, let's get started. And let's have a look. The first thing that I remember we were talking about in the last time is that we're trying to keep this singular kind of naming going within our structures, of our callable structures. So within DAG dimensions, let's right click, let's go to refactor, and then we're going to rename, and we're going to just literally remove the S. So go DAG dimension. And then we'll just say refactor, which will then change the file everywhere that it's being called. Okay, so if we now go into dep node and we click up at the top, we'll see we've got object dimension has removed the S there from the import. That is perfect. Okay, sorry, here, DAG dimension, not DAG dimensions, perfect. But I've just spotted an error, which is going to definitely come out in our testing. This is meant to be a property. So let's make sure that you have property before the O, because otherwise we are going to get an error saying it's not callable. Essentially, when we do dot notation O, dot notation width, for example, we want to be able to, like with attributes, go dot A dot, and then the functionality or the property that we're trying to call. So let's do that quickly here. Let's put in the property below, above the O, so that we can call the object dimensions and the attributes as properties, and then press save. And now let's jump to our test folder. So within Nodal, if you open up the Nodal folder, open up the test folder, and then right click on the tests, and go new Python file. I'm going to call this test underscore DAG dimensions, or dimension, sorry. It's just too easy. It does slip off the tongue, maybe, and that's maybe a reason it should be DAG dimensions. But we'll keep a line now. We'll just try and keep moving forward with this kind of methodology. Perfect. Okay, and now let's move that to the end. Let's go to test attributes, and we're going to just copy everything down to the teardown within test attributes base. So copy everything up. So Control C. Jump over to our test DAG dimensions. And then we've got everything set up. And at the very top, we'll put a test for our object dimensions functionality. All right, we do not need to import our attributes, so we'll remove that. And let's name the class. We don't need the base either, because we're just going to keep this all within one class. Perfect. So we do need the attrs. We're going to probably be needing attrs at some point to cycle through and check that we're getting these correctly. We do want our sphere, but we don't need to move it around or create an offset group. We don't need our plane. So let's remove the teardown, deleting our plane. Okay, so we have our test attrs. Our attrs that we can test, our attributes that we have. The translates and the rotates. We have created a sphere, as we've been doing in the other tests. Got a cube, and we are then tearing down and deleting these. Perfect. If you just pause there for a second and make sure you've copied everything. And it doesn't really matter if we use DAG or dep. within these. We're going to use DAG just because we're going to use sphere, because these are items obviously with form. But you can also import dep if you wanted to then test nodes against making sure that they don't load. But that is something that we'll do later on, so it doesn't really matter. But I'd advise using DAG because we obviously want to check items that have form. Okay, let's jump over to our DAG dimensions. I'm dragging that across to make it easier to access. And let's click on the def, and then press Alt and J, hold that down, then right arrow to move across, and then Control Shift and right arrow again to copy the name of the function, and then press copy, jump back to our test DAG, paste all of those names, double tap the Control and hit the up arrow key. And now let's tab in and write def test and then underscore DAG dimension underscore. And then jump to the end and open up brackets, which then should give us that lovely self. Okay, last thing to grab within test attributes, scroll right to the very bottom and copy the if name is equal to main. And then we'll just take that back and we will copy that into our new module. Brilliant. Okay, we've got our structure that's needed now to test. Now we're not going to test the initiate, that will be inferred. We'll test the initiate functionality, but let's start off with our first test. Okay, we're going to test world matrix, so passes and fails here. So we'll copy that. We will go fail. So we've got two test cases we're going to go for here. And let's just comment out the rest of our code. And so here we really just need to do self.sphere.o.world matrix. And we want to assert essentially that this is true. So let's encapsulate this. Assert true. And again, we know that our sphere has form. It is a sphere item. It has topology, and it therefore should have a world matrix. And now we want to also test the fail case for this. So if we tried to create a node, and then if we create a node and then we try to test for that world matrix, what we're going to get, we've already stated within our code, is the value error. So we need to check for that value error. So let's jump over to test attributes. Let's check and see if we've got a value error. We don't have one in there. So let's steal another bit of code over here. We'll copy that over. We'll assert raises value error. We will then go self.o.world matrix. So essentially by calling this, we will get this error. With a different item we need to do, because obviously this won't actually get that. Sorry, my mistake. So we need to get a calculation node. And then we're going to see if we can find out if that has world matrix. So let's create a calc node. Let's go calc equals. And we will jump back to test attributes. We'll grab a calc. Let's have a little look. Where is one? Let's search for calc. So Control F. Oh, here we go. That'll be perfect. We'll just grab our node here and we'll grab the delete. So Control Shift and Alt and double click. Control C to copy. And then we will Control Shift and down. What we can do is even just try to see assert false, just to raise it within an item that is actually checking for something, within a function, within a class that is checking for something. So we have world matrix passes. Now, we know this one should pass. We'll test it in a second. And then we're going to get a calculation node of scale x, or the cube scale x against the sphere scale x. And then we're going to test that node for world matrix, which again should raise us an error. Let's jump over to Maya and test that. So if we go Control S, Control A, Control C, and then Control A, Control V, Control A, Control Enter. All right. 2 tests ran. Oh, we've got 2 errors. Let's have a look. Oh, okay. And no attribute within delete. Interesting. Okay, let's jump back to our code and have a little look. Object does not have a delete. We are creating a sphere. It's within DAG. And we're going sphere dot offset. We're not creating the offsets, of course. So we're trying to jump back to an offset which doesn't exist and then delete it. So that will fail our tests. Okay, press Control S, Control A, Control C. Let's jump back to Maya. Let's clear out our output windows. Let's clear out these items. And now let's press Control V, Control A, and Control Enter. 2-ran. There's our beautiful dots of truth. And everything's run perfectly. Okay, perfect. All right. Let's jump back to our tests. And let's try to go through and test these sections here. Let's have a quick look. Okay, perfect. All right, so what we're going to do is we're going to test the bounding box, so the dimensions of our object. The expected result that we're going to get with our sphere is that it's -1 on the minimum of each one of the expected results here for the bounding box, and then 1 for the maximum, because we're creating the sphere in world 0, essentially. We're giving it the defaults that it's letting us run through with, which again is, we could put down radius, we could put, and again, the width, the height of the box, just to confirm that. But at the minute, we know, we know that the defaults are set here. So we're then going to round down just in case we get any very minute floating point numbers. But we are then going to cycle through each one of those items and just, again, confirm that this is the expected result that we get from our bounding box. Okay, and then within the DAG dimension bounding box, here's another way of testing. Essentially, what we're looking at, we're going to make a lambda, a one-line function of our bounding box call, and we're going to do the same for our bounding box property, which is pointing towards our bounding box here. So BB, that is essentially pointing back to bounding box. So we're going to confirm that those are aligning by getting the code and saying, well, are these actually asserting that these are using the exact same code? So what this is shorthand is, again, our dunder method here is going _code. It's going to read the code, and then it's going to give us human readable Unicode. And it's going to allow us to essentially confirm those strings, Unicode, against each other. All right, which is a good way of testing when you have objects pointing at each other, that they are actually testing the exact same code. And then again, so we've got one test for the code itself, that it is doing what it says, and another test for another function that is actually using the exact same code. So if either of these fails, if the first of these fails, the dimension xform bounding box, then we know that the functionality is broken. But if the DAG dimension bounding box, or BB, fails, we know that actually it's not pointing at the same function. So we need to go through and check that code. Okay, let's have a little look now at width, height, and depth. So what we're going to assert here, again, we're going to have a little look through. We're going to assert that the width of our sphere is 2, because again, we know the radius is 1, that is the default. And we're going to confirm that again. We are going to assert that the height of the sphere is 2. And we're going to assert that the depth is also 2. As it's a perfect sphere, it should essentially always be rounded down in 2 decimal places to being 2. Okay, and then we're going to also go through the cube and check that, which again, going through its default width is 2, and we're going to assert that. All right, perfect. Well, 3 with the depth here, which let me have a quick check. Yeah, no, that'll actually be wrong, won't it? Because we haven't set that yet. So we're checking our sphere as a perfect sphere, but let's actually set the height width. Let's actually set all the parameters up here. So let's go back and we will go radius equals 1. And then for our cube, we will go the width equals 1. We'll say the height equals 2. And then we'll say the depth equals 3. So 1, 2, 3, nice and easy to remember as we're going through it. And that will mean that as we're going through and testing, that we know that we're also getting something which isn't just a 1 or it isn't just a 2. We're getting some different parameters which we know we have set. Okay, perfect. Let's go Control S, Control A, Control C. Jump over to our Maya. Control A, Control V, Control A, and Control Enter. 7 tests ran in 0.045 seconds. Okay, perfect. They've all run. We've got no errors. Excellent. Okay, let's jump back. Now let's have a look at center and center position. Okay, perfect. Now, again, what we're doing here is we are essentially just checking 2 items against each other. And what we can do is just look back and just check that they are pointing at each other as expected. Oh, and we have a nice little error here. So we're going to get a circle dependency here. We're going to reach a maximum number, essentially, of calls that Maya can, Python will be able to do, because we're actually calling ourself as a property. But what we want to do here is actually point at the center written in the English way with RE rather than ER. Okay, and that will make sure that those tests are calling each other. Perfect. And what we can do is steal our code from above. Go test center. So we've got center and then center. And then this will make sure that they are both getting the exact same result. Okay, but within test center, we're essentially, again, rounding down to 2 decimal places within the X, Y, and Z we're getting back. And we're checking that the center of our item is at 0, 0, 0, because we know that we haven't moved it. We haven't changed its position. Okay, and you could probably also move either the cube or the sphere and then assert that its new position is what you moved it to. But I'll leave that to you if you'd like to do that. Okay, perfect. So we've got our 2 tests here. Let's also now test our DAG dimension position. Okay, so here we are going to actually do as we just said, and we are going to move that position of our object and then confirm that the position is actually returning a different position. So we're asserting our position in XYZ in translate and rotate. So translate XYZ, rotate XYZ. We're going to now confirm that if we set each one of those attributes using our self.attrs, if we can set those to a 1, we're going to assert equal that the sphere.o.position is all going to be 1. It's all going to be in 1s in that list. So that's a good, easy way of testing that. Let's go Control S, Control A, Control C, jump over to Maya, and then say Control A, Control V, Control A, and Enter. 10 tests ran in 0.075 seconds. Perfect. All right, let's jump down and let's check our pivot functionality. Next, we are going to test copy to. Now, we aren't going to test copy pivot because we're going to test that through copy pivot to, copy pivot from. You can obviously write a test to do that as well, but at this way, we're just going to test it through both of the use cases essentially. And what we're going to do is we're first going to start by creating a temp DAG group. We are then going to set the sphere translate X, Y, and Z to 1, 2, and 3. We are then going to move our temp DAG to the sphere. And then we are going to assert that the center of the temp DAG is at 1, 2, 3. So we now know that that is where the pivot of our sphere is because we've moved it over there. We are then going to copy the pivot from our cube, which is still at world 0, move our cube, move our temp DAG to our sphere's new pivot by saying move to, and then assert that the new center is at the copied center, which is at world 0, copied from cube, and then we will delete temp DAG. So we could just assert this straight through to sphere, but what we're not doing in our functionality is zeroing out the attributes or making sure that the attributes are zeroed out and then moved to correct world space. We're essentially just setting them and moving the pivot. We are not doing any other functionality, which you can add yourself. But at the moment, we are just essentially moving the pivot and doing some very simple logic. But okay, let's copy that over now to copy pivot from, and we're just going to then have to change over a couple arguments. So we're going to change the order of sphere and cube. Perfect. And then again, we should be able to say that this that this logic should work the same, because essentially we are doing the exact same thing, but we're now just copying in a different order. All right, let's copy all this code. So Control S, Control A, Control C, jump over to Maya, and then go Control A, Control V, Control A, and enter. 12 tests ran in 0.1 seconds. Amazing. Okay, it's good. Let's jump back to our tests, and let's check and test the center pivot, both the versions of the center pivot. Or actually, you can write this one yourself if you need to, or if you'd like to check that. But what we are also doing is making sure that center pivot, we also know that center pivot is essentially calling our center pivot functionality. So yeah, let's just check that that's all spelled the same. It's easy to miss these kind of little things. So we're checking center pivot, click through it. Yep, it takes us back. Great. We're not pointing at ourselves. Okay, good. All right, let's jump back. Now let's start writing our code for center pivot. I think we're going to probably actually start off, we'll set some attributes again. So let's copy out that first bit of the code. Then we will copy essentially pivot from, actually, yeah, we'll copy pivot from, and then we'll also then check that the pivot has been changed. Okay, perfect. So again, we are going to set our spheres translate X, Y, and Z to 1, 2, and 3. We're going to then copy the pivot from the cube, and then we are going to center the pivot. So what we should be left with again is the position of 1, 2, and 3. Because if we remember, we are moving it to world 0, which would then move the pivot back. But then if we center the pivot, we should then get it back to being 1, 2, and 3 in that position. We can check that again by creating a DAG and moving it as we change over the position. And that probably will actually make it a little bit clearer, because obviously where we're not zeroing out the attributes, that's probably not the best way to do it. So let's quickly copy some of our code down. Let's copy the delete DAG. Let's copy the DAG. Okay, so there we go. We've got a bit more of a comprehensive test there. We're creating our DAG node again. We're setting the sphere attributes. We are then going to copy the sphere from cube, move the temp DAG to the sphere position or the sphere's pivot, and then assert that that is at 0, 0, 0. And then, okay, what we're going to do is go center pivot. And what we're actually then going to do is remove that. We're actually going to copy that methodology again and go to moving the DAG back to the center of the pivot. Because we've now centered the pivot, we should be back at 1, 2, 3, and then say we are at 1, 2, and 3. Now let's see if we need to round down our numbers, or if that is enough for what we need. So let's comment out that last code here. Actually, let's delete that. We're not going to make 2 test cases for the same thing. And then press Control S, Control A, Control C, jump back to Maya. Control A, Control V, Control A, Control Enter. 13 tests ran. Oh, yeah, you see the annoyance here why we have to round down, because Maya has gone for this crazy floating point number. Ironically, 2 is the same, but then we've got 2.99999. Okay, so let's go back and we'll round down our numbers. So we'll go round I, and then we'll give that to 2 positions. Even 4 should be enough. For I in temp DAG center. Well, I need to close the brackets, the square brackets. Okay, and now this essentially should hopefully give us a rounded down number to close enough to these. Here we go. Let's say so. Control A, Control C. Let's jump back to Maya. Control A, Control V, Control Enter. 13 tests ran. Okay, perfect. See, 4, rounding down to 4 is enough to then get them all to a line. Okay, 13 tests ran perfectly in 0.1 second. Amazing. Okay, now let's test our DAG dimension distance 2, which is an awesome bit of functionality with a few other bits as well you can add to it. Again, you could do distance 2, you can do distance from, distance between, where you can add a list of items and then which will then cycle through each one of them using this functionality and just add all of those distances up together. You can do distance along curve. You can do, there's a lot of functionality, remember, you can add to items. That's distance along surface. I'm just giving you again all of the code that I've written. There's a lot you could do here because you can obviously set this to work around polys, and you can then go with distance between polys, distance across poly surface. There's so much logic you can do here to just help your own scripts to be able to then figure out, for example, with distance along poly surface, for example, I use that to then do weighting fall-offs, which then means that I have to do a lot less work on my weighting fall-off. So I can just automatically set the blink of an eye to be weighted between 5 or 6 polys or between 2 points that I've already stated on the screen. And then it'll fall off between those. And then using the math module, I can set the tweening of that. I can set it to be a nice Bezier fall-off essentially between those 2 points, making the weighting look very natural. And then because it's always done with math, because it's always done in a logical way, the weighting's then always perfect within those circumstances I've set it to be, because we're doing it with code. And if there was ever a circumstance or a use case scenario where it isn't perfect, hey, I rewrite that. Then I'll make sure that we have a catch for that scenario, and it also then works perfectly. So, okay, to summarize, write code. Optimize your code, write often, write beautiful code. All right, let's write our test case here. Okay, now a very nice and simple test because both objects in the world are at 0. So what we are going to test is that if we move the cube, translate, and we set to the arguments 0, 10, and 0. Actually a good little test for translate because we've got x, y, z. We're actually going to move it up in y. We could obviously just set y and then just remove that and just do 10, but I thought I'd show you another way of actually accessing this. So we're going to set translate to being 10, assert true that now the distance from sphere to the cube is 10. Okay, it's nice. It's very straightforward. I could just do a set equal. Actually, this probably makes a bit more sense here. And we will change the equality operator to being a comma. So now we are just going to assert essentially that these are all, as we've said, that they are going to be 10. So we're then going to set the cube to being off in x by 10 and set the y and the z to being 0, and then check again that is equal to 10. Let's actually check something different just to, again, have a different use case. Let's check 150 now. Perfect. Okay, let's copy all, jump over to Maya. Okay, let's clear out our windows using the clear all icon. Okay, Control V, Control A, Control Enter. Do we have any errors? No, 14 tests ran. Perfect. Okay, beautiful. So we're now testing all of our functionality. Essentially, no, that does need to be 2 lines, doesn't it? Okay, within our class, test object dimensions. Okay, and what you can do is just close your Maya and then reopen. And what you can then is look and test all of our test cases to make sure that they're all running as expected. But just remember, what we're testing here is actually incredibly powerful. What we're looking to do is to make sure that our functionality is working as expected. And as I said, as you're writing more complex functionality, as I kind of gave you a little hint towards with the distance 2, you'll need to write more and more kind of difficult to write tests. So you will need to write a lot more functionality within a test. If I'm testing across a certain amount of polys, I'll have to test a sphere, and then I will have to be able to confirm what the distance is across those polys. I'll need to be able to get a curve and make sure that I know the exact length of that curve, and then test the length of the curve. You want to make sure you curve, that you move the points of the curve so you are curving it, that you are able to then assert what those lengths are. But these are all very powerful things to be able to do, and are best for you to be to get used to doing. Those tests, I've got tests that probably are about 40, 50 lines long themselves, because you do have to just write functionality out. But again, a lot of those can then be shortened by me writing better base classes for those tests. So don't worry if those get a little bit crazy. You can then just get default. You can start importing mesh into an object base that you can then test, that you can maybe create curves, create things that you know certain parameters of, that you can then test against for extreme test cases like that. Okay, let's jump into Maya. And now let's hit the test button. Brilliant, 121 tests ran, okay, in 1.154 seconds. Okay, great. We are showing that everything is working exactly as expected. That is awesome. Well done, guys.